Now that we have understood the MAX98357 hardware schematic and even explored the data sheet, it's time to make things actually work. In this video, we are going to play a wave audio file using the ESP32. And the best part, no external SD card required. Everything runs directly from ESP32 flash memory. And yes, as always, I will walk you through the code step by step so you not only use it but actually understand what's happening behind the scenes. Namaste and welcome back to Avinashee Tech. Alright, first things first. Let's quickly go through the connections. The VDD pin of the amplifier is connected to the V-in pin of the ESP32 and of course ground goes to ground. Now the ST pin is connected to GPIO 5. This gives us software control over the amplifier. We can enable or disable it directly from our code. Next, the gain pin is tied to ground, which according to the data sheet sets the gain to 12 dB, a safe and clean default for most use cases. For the I2S interface, we are keeping things consistent with our previous videos, especially the ICS 43434 setup. The data line or DIN in this case goes to GPIO 21, BCLK is connected to GPIO 14 and LRCLK is connected to GPIO 22. Finally, on the output side, speakers positive and negative terminals are connected directly to the screw terminals of the amplifier. And that's about it, pretty straightforward. Now let's jump into VS Code where the real action happens. Inside the I2S header file, we just have the basic definitions and function declarations. Nothing too fancy there. The interesting part is in the source file. This time, instead of an RX handler like we used with the ICS 43434 microphone, we are working with a TX handler because now we are transmitting audio data. This TX handler will be important when we move into the setup. In the I2S setup function, most of the configuration remains very similar to what we used earlier for the microphone. We still have master mode, 16 kHz sample rate, 16-bit width, and the standard Philips I2S format. LRCLK polarity and GPIO configurations are also along the same lines. The key differences start here. The mode is now set to stereo and slot mask is configured to use both left and right channels. Next, we allocate a new I2S channel using the TX handle we defined earlier, and this channel is then initialized and enabled for transmission. After that, instead of a read samples function like we had for the microphone, we now implement a write samples function. Here, we use the I2S channel write API to send data from a buffer along with the number of bytes we want to transmit. Moving on to the main application, we start with SPIFFS configuration. If you are not familiar with SPIFFS, think of it as a lightweight file system that lets you store, read, and manage files in a specific region of flash memory. On the ESP32 dev board, the module you see with RF shielding already includes a 4 MB flash chip. This flash communicates with the ESP32 over SPI, more specifically QSPI. So instead of dealing with the complexity of an external SD card, we can simply use this onboard flash for basic testing and storing small audio files. To make this work, we need a Partition.csv file. The first 3 entries of this file are standard in most projects. The last entry is what we care about. It's of type storage and we name it SPIFFS. The offset is automatically calculated and we assign it a size of 1 MB. In addition to this, we create a separate folder called SPIFFS file, and this folder contains the wave audio file that we want to flash into memory and later playback. One important thing to remember, wave files are much larger than MP3 files, so make sure your audio file size stays under 1 MB, otherwise it won't fit into the allocated partition. Now, in the CMake lists file of the main project, we add a specific line. What this does is it takes all the files inside the SPIFFS file directory, creates a SPIFFS image, maps it to the storage partition and then flashes it onto the ESP32. The good part is you don't need to handle this manually when you flash your main project. This step is automatically taken care of. Coming back to the main function, in the SPIFFS configuration, the base path is set to /SPIFFS. You can think of this as a mount point, which is similar to C drive in Windows or the home directory in Linux. The partition label is set to null, which means the system will automatically use the first partition in the table that has the SPIFFS subtype. And if mounting the file system fails, we enable formatting as a fallback. Once this configuration is registered, we open the audio file from the mounted directory with read permissions. If the file is missing, an error message will be printed. Next, we configure the GPIO for the shutdown pin. Both pull-up and pull-down resistors are disabled and the pin is set to open drain output mode. If you remember from the datasheet, the SD pin can be driven using either open drain or push-pull configurations. Now, as discussed in the previous video, this particular board already has a 1 megaohm pull-up resistor connected to the SD pin by default. And that's exactly why we choose open drain mode on the ESP32 side. After that, we call I2S setup to initialize I2S peripheral. Before playing the audio, we skip the initial few bytes of the wave file. These bytes correspond to the header, which contains metadata and not actual audio samples. Next, we set the SD pin output to high. In open drain mode, this effectively puts the pin in a high impedance state, meaning it doesn't override the default pull-up. As a result, the amplifier remains enabled. The audio channel configuration is set to mono output, so even though we are sending stereo data from the ESP32 side, the amplifier internally performs a down mix, essentially combining left and right channels into a single output. Now comes the actual playback. The wave file is read in chunks and stored into a buffer. As long as we haven't reached the end of the file, this buffer is continuously written over I2S in a loop, streaming audio to the amplifier. Once the file ends, we pull the SD pin low. This actively drives the line to ground and puts the amplifier into shutdown mode. Alright, that's enough with the code. Now it's time for some hands-on. Let me first show you the wave audio file that we will be storing in flash and playing back. The original file was in stereo with a 44.1 kHz sample rate and 32-bit resolution. I have simply downsampled it to 16 kHz and reduced the bit depth to 16 bits. After that, I made sure the file size stays within 1 megabyte. If by any chance your audio exceeds that, you just need to trim the audio to fit within the limit. And that's pretty much it. Once the file is ready, we just place it inside the SPIFFS file directory. Alright, now let's open the terminal, build the project and flash it onto the ESP32. Once the connections are in place and the board is powered up, and there we go. You can hear the audio playback. So that was a quick hands-on tutorial for the MAX98357 digital amplifier. This would help you get started quickly with testing this chip along with a basic understanding of what's actually happening in the code. If you found this useful, do like and share the video and consider subscribing to the channel. This is Avinashee Tech, signing off.